In this video, we're going to take a look at a salt where the salt is actually derived from weak acid, weak base. So in previous videos, we saw that one component was derived from a weak component and one from a strong. And there it was pretty straightforward because we just made an ice table with whatever was derived from the weak component. Now we're going to take a look at a situation where you have a weak acid, weak base salt. So here we have ammonium fluoride. We're going to make ammonium fluoride dissociate. And when we do that, let's do a proper dissociation equation. When we do that, we get NH4 plus AQ plus F minus AQ. So we have to test out both of these salts here. So let's test out the NH4 plus. First, we've already kind of done that before. NH4 plus, as we know, when you react it with water, will make NH3 plus H3O plus. So this will happen because this is a weak base, and this is the salt of a weak base, therefore acts as an acid. Okay, now we're going to do the same thing, but with F minus this time. So this affects pH. F minus plus H2O, liquid. If this were to happen, the H would go with the F because H is positive, F is negative, and then we'd have some OH. Now be careful here. Students often see HF and they say it's a strong acid, therefore no effect on pH. That's not true. HF, let's go look at our table here. HF, hydrofluoric acid. Let's find it over here. Did I miss it? Hydrofluoric acid does not have a very large Ka. It's 6.3 times 10 to the power of negative 4. So hydrofluoric acid is actually a weak acid, not a strong acid. So it's a big misconception. So this is a weak acid. This is the salt of a weak acid, therefore acts as a base. And the reaction does happen. So both of these affect the pH. This will act as a weak acid, and this will act as a weak base. So how do we know where the pH will be? Will it be above 7 because of the weak base or below 7 because of the weak acid? Well, it depends on the Ka and Kb of the substances there. So what we need to do is we need to find the Ka of ammonium and the Kb of the fluoride ion and compare them to each other. Once we compare them, then we can figure out if the solution is going to be acidic or basic. And I'll show you the different results. So let's go find the Ka of ammonium. So Ka for ammonium, which is NH4 plus. We can probably find that in the table. Ammonium right here, NH4 plus, 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10. Okay. Now we need the Kb of fluoride because fluoride is acting as a base, so we know we're looking for the Kb here. How do I know it's acting as a base? Because in our equation we saw fluoride is producing some OHs. So we're looking for Kb. So I have to go in my table to find the base fluoride. But if you look carefully, you don't see fluoride. That's okay. We have a relationship. Kw is equal to Ka times Kb. So as long as we know the Ka for the conjugate acid, we can find the Kb for the conjugate base. So 6.3 times 10 to the negative 4. Okay. So we know that Ka times Kb, that's multiplication, is equal to Kw. Therefore, Kb is equal to Kw over Ka of the conjugate acid of HF. So that means our Kb is going to be 1.0 times 10 to the negative 14 over the Ka of HF. And as we saw, that was 6.3 times 10 to the power of negative 4. And so when we get that, we get, so let's do that in our calculator, 1 times 10 to the power of negative 14 divided by 6.3 times 10 to the power of negative 4. And we get 1.5873 times 10 to the power of negative 11. We don't really need that many sig figs. We could keep it to 2 sig figs. So we could say about 1.6 times 10 to the power of negative 11. We're just keeping it to the same number of sig figs that most of our Ka values and Kb values have in a table. So we need to compare them now. We need to see which one's larger. There's 3 scenarios you can see. If Ka is equal to Kb for the weak acid, weak base scenarios that we're looking at here, then the pH will be 7. If Ka is greater than Kb, then the pH will be less than 7 because your acid is a better acid than your base is a base because your Ka is larger. And if your Ka is less than Kb, then the pH is greater than 7 because your base is better at being a base than your acid is at being an acid since you have bigger Kb. So in our situation here, this was our acid because Ka, and this is our base because, well, Kb. We can see the Ka is greater than the Kb. So that leads us over here. So since Ka is greater than Kb, the pH will be less than 7. Now, there actually is a way to calculate the exact pH. You could theoretically just set up an ice table for whichever one was higher. So we set up an ice table for ammonium and then find the pH there. But there's actually more steps you need to do. So in general, for a weak acid, weak base salt that has both weak components, I would just expect you to be able to predict where the pH would lie. Would it be below 7, above 7, equal to 7, based on your comparison of the Ka and the Kb? We won't see these as often in grade 12, but it's still good to know in general where the pH lies by comparing the Ka and the Kb to each other. So in this video, we saw how to determine or estimate where the pH would be for a solution that has a salt, which is derived from weak acid and weak base components. So there's no strong acid or strong base component, so both parts will have an effect on pH. All the steps were the same, but the main difference you'll see is that both parts have an effect, and as a result, you need to find the Ka and Kb of both parts and compare them to make your general conclusion. But we wouldn't expect calculations for this part here because it goes beyond the scope of the course that we need right now. If you do want to see additional problems related to this weak acid, weak base, you can go to your main handout over here. And I did include an additional video that goes through some more cases that we described There's more cases where Ka may be smaller or Ka and Kb might be equal to each other, and you can try those out at this video link over here.